Good morning, everyone. I hope you guys rested. I hope you didn't stay the whole night just solving a small problem in here. What I'm going to do with that problem, we were just talking about that I needed to evaluate you at the end, or by tomorrow, right? We got a test. So whatever you did in here is going to be some mark for that final, okay, for the final thing. Whatever it is you did, the effort, to try it. So what I'm going to be collecting is probably the table. If you can just put your name on it, right? If more of one word together, please put the two names in there and just handle them to me by the end of the day, okay? So that tomorrow we're going to have the composite results in here, and we're just going to see what happened, all right? So that's going to be part of your evaluation, and this just evaluation, effort, all right? Do you guys have any questions in here? Okay. What we're going to be looking at today is we're going to switch gears from C-pitch analysis to the shear strength analysis, right? Shear strength also is a very important area in which geotechnical engineering and pavement engineering we're going to need to, be very expert on it. And I'm going to try to do, again, what I did on the C-pitch analysis. We're going to try to get the basics to you for you to understand why we use this equation and see at the end a couple of examples of how we can use, okay, these equations, these concepts, I will say, right? So we're going to talk a little bit about the stress state variables that are responsible of the shear strength behavior of the soils, of the unsaturated soils, and I've been already talked about that briefly. And then we're going to talk about the shear strength of unsaturated soil, the questions that are available, how do you measure, and again, how you can estimate it, right, if you don't have access to measure it directly, right? So this is the way we're doing today again. So we're going to start with the stress state for the saturated soils, which is you're familiar with that. So you're going to see that how this one is a special case of the unsaturated case, actually, right? Instead of being the most important, the saturated case, the most important is your general equation, and then one of the conditions is when you, special cases when you have saturation equal to 100, pretty much, right? A brief history of how we measure this one and how these things start evolving, and I'm not going to show everything that everybody had done since the 60s, I guess, but I'm going to bring elements that they added to the theory that were very important at that point, right, for us to have whatever we have today. The shear strength equation for the unsaturated soils, how to determine that in the lab and how to predict it if we don't have lab data. Okay, so back to Terzaghi. Carl Terzaghi is our father, the father of soil mechanics. Everybody knows and hear about Sol Terzaghi if you are in graduate school in geotechnical engineering. And he postulated his effective stress principle to describe the mechanical behavior of the saturated soils on shear, right? And this one is a very well-known equation, 1936 we're talking about, okay, almost 100 years. And this one is the effective stress equal to your total stress minus forward pressure. So that's how everything started. Like when he started putting equations to the soil mechanics, we became a mechanistic, group of people working, mechanistic engineering group. So what are the strengths of this? It's applicable to all sands, silts, and clays. It was good for that when you get into the saturated. There was independent of soil properties, so it became a constitutive, relation, not constitutive relationship. Constitutive is when we put the soil properties in there. But it was independent. There are the stress state variables. Remember, a stress state variable is a variable only if it's independent of the material properties. Okay, only if only it's independent material property. It's what you apply to the soil. You know, the soil has no idea what is coming. Okay, it's receiving something internally or externally, right? The environmental meson changes, and the suction is an internal stress that is changing, right? It's totally independent. Same thing for the normal stresses or the applied stresses external. So these are stress state variables and can be applied independently in each Cartesian coordinate. All right. The disadvantage was was too much emphasis placed on this equation in such a way that the effective stress became the great deal for us, and we didn't do better than that. All right. So, and the source of effective stress was not known. We said, okay, we got total stress, forward pressure, but there was no studies about all of these internal forces that work together for the effective stress to go. Okay. So I'm going to go quickly on that one. You have the information. You already got the slides for this today? Okay. Thank you. A little bit quickly on that, but again, I just want you to understand, the evolution of that since the 1940s, when Bayard says, okay, he started with the theory of consolidation, and he said, okay, we got now occluded air bubbles. Okay, so you need to understand that the theories for continuum mechanics, you have to have continuous flow of water, continuous flow of air for that to work. When you start getting into the occluded thing, you're going to need to start working on discrete elements analysis, stuff like that, which is not the same. But nevertheless, he started with that, and he highlighted that there could be a separation between the total stress and the pore water pressure changes, okay? And then Coleman suggested that you can start combining those stress states, sigma 1 and minus sigma pore air pressure, or sigma 1 minus pore water pressure, or sigma 3 minus pore air pressure, or pore water pressure minus pore air. So he tried all of these combinations, right? Because we needed something easy to measure for us in the laboratory, okay? And that was the idea of combining stuff so we could measure that, okay? And this one is the assumption that was used to start doing the constitutive relationship that we have. Then Bishop, that we saw the question that I don't like, okay? But Bishop did a great amount of work. I mean, he measured, he started putting together the testing. I mean, he postulated a lot of stuff on this unsaturated soil mechanics, 1963. He observed that when he started changing the moisture or the suction in the soil, changing the moisture, drying or wetting, the volume change behavior was different than putting a load on it. All right? So he said those two have to be independent stress state variable. You see the concept is pretty important on that regards, right? Then Matthias and Radhakrishna start introducing the concept of state parameters, right? And again, everything started with volume change behavior, and then we just get into the shear strain. I went a lot on this one, but okay. There were some other people that started working on that, and again, it appeared that the matrix suction, when we have it different from the net normal stress, was working very good, okay? And one after the other one, they were just publishing more and more on how if you divide those two variables, you will be able to, say how the soil will behave. And Friedland came in the 70s, which generated a theoretical equilibrium analysis for unsaturated soil elements, and that's the one I'm going to be quickly working on in here. And I say quickly, I'm trying to have as much as I can. But he considered the pore air, the air phase, the water phase, the solids, and also that contractile skill that Professor Barat talked the first day. The contractile skin is that, a skin between the water and the air, right? And basically, he also considered that in his equilibrium conditions. And he definitely, and he proved in several papers that the best combination was the net normal stress, the total minus pore air pressure, remember yesterday, and the suction, pore air minus pore water pressure. But they tried they tried many combinations. I mean, it's just not just boom. It was years of information to get to that point. So two independent stress tensors containing the stress state variables form the fundamental basis for developing a science for unsaturated solid mechanics. So that's how it started and how it was evolved. And I didn't include many of the people that contributed to that. So we start now getting to the effective stress equations, all right? So 1958, Crony started with the effective stress equation again, and he started putting a parameter, right, beta prime, right, to the forward pressure. He said, okay, if I just vary that beta prime, right, and just make this guy less, I want to have higher effective stress, which is what happens, right, when you dry your soil. You're going to have higher strength. So, and then Bishop came with the equation. This is the one that became very famous. Not only that, because he used the two stress variables were fundamental and were correct, but then his famous chi value that everybody adopted, right? Like good. But again, I want to show you these shortcomings for that equation. Then Richard, not the Richards from the Richards equation, he came with this kind of formulation when you have a chi m, which was the effective stress parameter for matrix suction. This is the matrix suction for air. And this one is another effective stress parameters for the solute suction, okay? Just linked to the osmotic suction in that. Right.
So C is also.
Yes. In that case, this is the way he formulated, but it is the osmotic component. So he started adding that osmotic component there, which is important for some applications. So Bishop equation, again, I just talk a lot about, but Blight is the one that convinced, everybody, all the scientific community, 1 year later after the equation, that chi parameter was also a function of the degree of saturation. And if the degree of saturation was a function of suction, it was kind of a mess in there, right? A mess in there. And they said, well, the results show for different compacted soil that there was also a scatter in the relationship between the chi and the degree of saturation. And everyone was independent of each other. So it wasn't a single value effective stress equation, which he critiqued at that time. So for the effective stress approach for unsaturated salts, up to that point, there were several equations that have omitted the effect of pore pressure. If you didn't see, okay, they put in there, put it atmospheric, 0, and that's okay, what we do, but suction is a function of that, right, whether we put it at 0 or not. All the equations were constitutive in character, in that the salt properties were incorporated later to put the constitutive relationship, not part of the stress state or the stress variables. But all of them violated the fundamental principle of continuum mechanics. So in order to have a good solid stress state variables for unsaturated soils, these were the selection criteria that Fredland used for that. The variables can be experimentally tested, something that we cannot test as engineers. I'm not going to use that thing, okay? He said, we need that. Variables can be theoretically justified using equilibrium considerations, okay? So we're going to have continuum mechanics applying to this one. Variables were the component stresses that can be measured in engineering practice, and variables that meet the requirements set out by the definition of state variables in continuum mechanics, okay? It's something that all the equilibrium considerations will apply. So what it was done, it was that the variables that they used, he said, okay, the stress state variables can be taken as, okay, first of all, it has to comply with the equilibrium of one phase, like the solid phase, for example. Remember continuum mechanics? Okay, I'm going to show you in a minute. And also, every one of those phases have to be at equilibrium, all right? Have to have an equilibrium condition. Water phase equilibrium, air phase equilibrium, and the contractile skill equilibrium. Okay, so this one was a fundamental thing for them to postulate that. And I'm just going to show you here. For example, this one is the equilibrium equation for the one-phase soil, okay? And he said, okay, we do have two forces that are going to be there, obviously the body force and also the surface forces, right? This is what you've been learning for one element, discrete element that will just get the continuum mechanics. And those stress vectors on the surface on a particular phase of the elements are the limiting values that you're going to have. So you're going to consider one of these elements, and whatever stresses you got, are going to be an extra stress as you get out of the other phase, right? The delta. So they use a cube for a free body diagram, and basically representing the whole elemental volume of the soil. Okay. So what you got in here was, in every phase, you're going to have the shearing stresses, right? And you're also going to have the normal stresses for that. And basically, he postulated, remember, it's just for the solid, right? No water, no air, nothing. All right? So just for the solids. So he formulated, based on conservation of linear momentum, the equation in one of the directions. This one is, for example, of the shearing stresses that you find, the normal stresses in here, the gravitational stress, and basically this one is an acceleration term that if you assume no acceleration of the soil, that can be zero, right? This one is the acceleration, that's the velocity, and then you ended up with the stress tensor that you all know, right? You all know in the three-dimensional analysis. All right, so it's the same thing. So it applies for a saturated and unsaturated. Equilibrium in the solid phase must occur, right? And you have all these subscripts depending on the direction of your. So it's a three-dimensional analysis. Then they went into the independent phase equilibrium. Okay, each phase in the solid structure is independent from one another. Extra independent from one another, right? This is because each phase has its own independent properties that independent, they're linear, they're continuous and coincident. This is the whole postulation, right? So they have to be independent of each other. And then what we do is we use superposition, okay, on all this equilibrium analysis. So the areas or the volumes that are associated with each phase, what is done is being written down or related to the porosities, okay, to the porosities. So remember what the volume of voids is, of what, when you do have the volume of voids, or when you have volume of water or volume of air, right? There are, porosities, right? Porosities within the soil. Okay. So this is done by using the porosity designation for the volume. And let's, for example, in here, a water phase equilibrium analysis, in which you do have, in this case, again, you just said, okay, this thing is going to be saturated. All right. This is the water. That's the water equilibrium analysis. And this is the equilibrium continuum mechanics analysis. And basically what they do is, okay, what is the interaction of the body forces between the solid and the water? Okay, I only have water around it. Okay, and basically they use an interaction force between those two, and then also use the continuum with the porosity, right? The porosity of the water times the gamma of the water, and going over the other side with the infinitesimal, change on that one, right? So you do the summation of equilibrium on the one direction. The interaction force between the water and solids is kind of a C-pitch force, and it's right here. And basically, this equation is the one that you use that will result in the effective stress equation. Total stress minus pore water pressure, right? That's basically the equation that you're going to be using for that. Same thing they did for the air. Okay, now you got a solid, the element of solid, and now it's interacting with air. And they did exactly the same, the equilibrium analysis for the air, okay? In this one, so basically they assumed that the soil was completely dry, two-dimensional phase system, solid and air only, and the equilibrium equation can be written for the air phase the same as the water phase. Probably you don't have that slices, right? Because I saw some were interested on this, and I add them at the end. So I don't know if you don't have them, I can just give it to you later on. Anyway, so I just to show you the way that they were doing, this one. So they were equilibrium analysis. The contractile skin usually was taken as part of the solids, okay? That's one way of looking at that. There were some physics around that by several authors, but I think Fred Land got all this one and figured out that the interaction was, could be taken, the skin could be taken as part of the solid. Okay, so that's how he did that. But nevertheless, all this, okay, what is the contractile skin? Here is this. Okay, so that's influenced the solid structure by its ability to exert the tension between those. Professor Barar already explained that to you. This is a wearable soil, that the contractile skin is kind of concave for that. And when you have a repellent soil, the contractile skin is going to be kind of a convex, right? And then you're going to have that kind of stuff. In this case, for example, the ported pressure is greater than portward pressure, so the suction is positive, right? Suction is positive. Then you're going to have this one going that way. The tension is going to go from the sides. And when the ported pressure is less than the portward pressure, you kind of have, going on the other direction, right? So this one is also, there is an equilibrium condition for that between the air and the water, which is the skin, right, the contractile skin. Now forget about the solid, and now you got water and the air going on in there, right, between those two. And basically, a constant degree of saturation condition was maintained for the soil, while the flow of the air and the water in the soil were kept independent to each other. And basically, the unit surface tension magnitude that you have in there, the constant, was constant at a particular temperature. Based on all of this, they put all them together, obviously, all the equilibrium together. Then they made the superposition by adding those equilibrium equations together. And they come up with this set of parameters that's the one I showed you the first day in class. That basically, this one is just for a two-dimensional, but you can put it on the little cube. This is the complete form of the stress state at a point for an unsaturated soil in a two-dimensional basis. You're going to have the normal stress minus ported pressure, the shear stress is going on in there, the port water pressure right there, and that's going to give you the whole, tensor. But this is how it is. It is pure continuum soil mechanics. Now, that doesn't mean that there are no other theories that will do that a different way and be okay, right? And just come out with something like that. But on continuum soil mechanics, that's the way they did it, all right? So again, I want you to be aware that there are some other ways of doing business, right, in terms of physics. All right. So how we use that on the shear strength of unsaturated soil? Now you do have the independent stress state variable that we're going to work against or in favor of you for analyzing shear strength, all right? And again, you need to realize that what the port area minus port water pressure is the I guess the environmental load that you're going to have in there, right? It's going to be that. And this one is the normal stress is your external load, your building, your whatever it is, your confining pressure, same as you have done that before, and obviously the shear stresses, right? So this is what you got. So there are many problems, obviously, in engineering that you are very well versed on that you need the shear strength of the soils to solve it. Right? Bearing capacity is one of them for the foundations. Lateral air pressure is another one, and slope stability, right? I do have very good examples on bearing capacity and lateral pressure, but I thought the first day that we introduced everybody is very, very likely invested in slope stability, right? So I just brought my little example on slope stability here, right? So this lecture, or this part of the lecture, will describe how the shear strength of unsaturated salt can be formulated in terms of those stress state variables that I just presented and the shear strength parameters for saturated salts. All right. So you need to realize that when we talk about K and SAT function, remember yesterday? That was a function of the salt water characteristic curve, right? Which is, the stress variable was there, the suction value, plus the saturated value, right? You needed to include that saturated value. This is nothing but, one corner that you need to fix, right, in order to do the whole function. Same thing in here. In order to do the whole shear strength, behavior, in terms of now we need two stress variables, not just one, right? In terms of net normal stress and the suction, we need to start with the saturated condition over the dry condition, right? So we need the saturated shear strength parameters, the C and the phi, or the C prime and phi prime that you've been working on since you start, your graduate school or even before that, all right? So this is the shear strength for saturated salts. You all are very familiar with that. This is the case for one of the models of many, many models that are available. This one is the Moore-Coulomb failure envelope for a saturated soil. It's a criterion that was, that Terzaghi again, 1936, and it's a straight line pretty much, which is actually been killing us because everybody thinks it's true, right? That's not true if you have a very wide range of variability, right, on the lower side and the high side. Again, that will give you a couple of parameters in there, the intercept between the shear strength and the net normal and the normal stress. In this case, it's saturated, so it's going to be your effective stress, right? Because your pore air and pore water pressure will be the same. So it's the same thing in here. And the phi prime value, right? It's a straight line again. I don't believe in cohesion either, right? For normally consolidated soil, for sandy materials, you have no cohesion. The only way that you start getting into an intercept in here is when you have over consolidated soils around here, and all your Moore circles will accumulate in here. It's going to make something like that, right? You see a dense material on that stuff, right? So this equation defines a straight line, represents the number of possible combinations between the effective normal stress and the shear strength of the soil at the failure plane. And basically, pore water pressure acts equally all over the planes, this, element that we show a little bit earlier. And the failure envelope is obtained by plotting the line tangent to a series of Moore circles, right, that you do for different stress conditions, right? The deviator stress in here, another deviator stress in here, you vary this one, and then you do your line. So this is the concept we use for shear strength for unsaturated salts, right? Two-dimensional, it could be three-dimensional. This one is sigma 1 minus sigma 3, but there is another one that is sigma, sigma 2 minus sigma 3, right? Sigma 2 minus sigma 1, I guess. For triaxial conditions will be the same. So we start with that, and then we start, okay, how we can translate this one into the unsaturated salt world, right? What we're going to be doing that. And 1956, Donald started working on a direct shear testing, okay? And basically what he did is he got a shear box. He modified that. He put a membrane, a colloidal membrane with, like air entry values. Just think about that, right? Has an air entry value to that. And basically he put that in there. The sample at the top was open to atmospheric pressure. So basically he controlled the pore air pressure, right, to 0. On the top, it was open to the atmospheric pressure, and at the bottom of the sample, basically, he created some suction. He created some suction in here with this, and therefore, he imposed some suction in there, and he was measured that. How he imposed your suction? Well, you can use a manometer, with some constant head overflow tube, and basically maintain any suction that you want to maintain in here to the vacuum. So the specimen was then consolidated the same way that we do for shear testing, and then he tested and started working on that. So we're talking about 1956, all right? So a little bit ago, not for us to be doing that in the lab. what he did, he found a nonlinear variation of the shear strength with respect to suction, right? He put this one, he put at different suction levels, and he's obviously with this kind of setup, you cannot go more than 90 kilopascals, right? You're going to start getting into cavitation because you're imposing a negative forward pressure in there, right? And well, I'm going to talk a little bit of axis translation in here in a minute, but basically this one is imposing a negative forward pressure, and therefore he didn't go far. But he shows like there was an increase in the shear strength as your suction start increasing. That's the important part of it, right? He didn't attempt to derive any equation on that, but he shows a very nice increase. And there was a point when it started to settle down, like leveling out or going down a little bit. And as a matter of fact, if you continue that for a second, that thing gonna go to zero, right? When you have higher suction value means zero water, right, between the grains. And what's gonna happen, right? That sandcastle is gonna go down, right? No water. So the shear strength will go all the way down again, right? It's gonna launch. Then Bishop, again, he did a lot of work on testing, on triaxial tests, and modified. He also modified that, and it's the same thing. You know, you modify that by putting a porous stone instead of putting the porous stone, putting a red entry value, right? In such a way that when you applied your suction value, you only allow, okay, water to go out, not the air, right? And that's the way that you were able to measure that. So, but what I want to show in here is that Bishop said, okay, we can do CD test, consolidated drain it, CU test, right, consolidate and drain, UU test, we can do uncompressive test, unconfined compressive strength, but also we can do what he called a constant water test. Okay, and I'm going to show you in a minute what is that. Then Escario comes in here, and what I want to show in here for Escario is that, okay, the axis translation technique. Okay, so he said, well, I cannot go like Donald, that you put suction at the bottom of your sample, right? Because after 90, I cannot measure anything, all right? So what he said is, okay, to me it's easy probably to say, okay, if I need this first. I'm learning, huh? See, so if you have port air minus port water pressure, and let's see, this is the suction value, right? And I'm going to put a suction value of equal to 150. Okay? So you can get that suction value by putting in here atmospheric pressure, open the sample to atmospheric pressure, minus putting a negative port water pressure of minus 150, right? You get cavitation, boom, it's difficult to do, but this is the concept, it's negative 150, right? Or you can do exactly the same by putting a ported pressure in here of 50 minus, and how much port water pressure you're gonna put in there? How much? Minus 100, right? And that's gonna give you the same 150, right? The same 150. So now you got 100 kilopascal. You are close to the point when you don't have cavitation. Or you can say, okay, I'm going to put in here a ported pressure of 100 minus, and how much will be your port water pressure? Minus 50, right? And that's going to give you the same 150, right? Here we go. So now you can do this by translating both stress states to a scale that you can measure in the laboratory, all right? And that's basically what we call axis translation technique, all right? And that's what we use on the devices that, you know, we got the odometer type devices, right? We impose a ported pressure of our suction value that we want. Okay, in this case will be 150. And then we keep our bottom, okay, saturated in contact with the water of the soil, and that is open to the atmospheric pressure. Therefore, the port water and the ported pressure are the same, okay? So port water pressure will be zero right there, right? Because it has no pressure at all. So basically it's minus zero here, and that's gonna give you 150. So for us, it's easy to just control the ported pressure, you know, control this one, and that's the way that we put our axis translation technique. Everybody understand that? And okay, I'm very sure. So this is what I want. Escario started doing that. In 1980s, he started doing the axis translation techniques, which were actually very good. And in order for you to have that, obviously you put port air pressure in that, and then you just want water to get out there, right? If you get air out of that port air entry disk, then you're going to dry your sample. You're not going to be able to get anything, all right? So he introduced that, the high entry disk that we were using. He applied any normal stress on the top, and he was able to do. And another nice thing is he started looking at, this is the net normal stress and the shear stress. And this one is for, let's say, the zero matrix oxygen, the saturated condition. And then he measured at 200 kilopascal. Now he was able to measure, now we're talking about 800 kilopascals, right? He was able to measure much higher suction values. And he found out that the shear strength will increase as your suction increased, and that the lines were pretty much parallel to each other. That's what he observed. A little bit different from this guy, right? Okay, so then Johan Fredland in the 1980s, what I want just to, again, this is a very nice history for you to read if you are interested on that, and I put all of that. But again, he found that for a planar failure envelope, the internal friction angle is assumed to remain constant under saturated conditions and unsaturated conditions. So no matter what condition you are in the soil sample, your phi prime kind of remains constant, right? Remain constant. So the contribution of the phi prime is independent of suction, right? Because it's a function of the frictional nature of your soil. So the effect of matrix suction is clearly shown in here. On if you keep this one and matrix suction in here will be the phi value will be this one, the first one, 33.4, and then you start increasing your suction, and you just measure what is the suction versus the shear stress, and you can see the contribution going up. And basically, he imposed also an angle on that and said, okay, the contribution now can be measured independently from phi prime, right? And now is, he called it phi b, phi super b or whatever, right? So this one, what I want to show in here, that's Fredland's model. And then he came out with this model, right? He said, okay, we do have the two stress state fundamental variables that I talked at the beginning, and you're going to have in here the C prime. Fine, we're just going to keep it in there for any reason that you got, right? You're going to have in here your net normal stress multiplied by your tangent phi prime. That's the contribution of your load. And this one is the suction contribution times tangent phi b. And this is perhaps the easier way that you can do the extra increase on shear strength due to the suction value, okay? So what factor is in there that difficult to find for you? Phi b, right? That's phi b. That's the guy, right? That's the guy, because the other one you know how to do it. C prime, phi prime, you know how to do it, right? You impose any stress state, those are independent of whatever you're doing. And the only thing you need is going to be the property on tangent phi b, right? What is that guy? All right. So this is the holy grail of this one. This is when everybody's been focusing later on. The good thing about this one is that that extends, or basically this one is the general case of the saturated case that you'll be learning always, right? Why? Because if you have a saturated soil, what is going to be your suction? 0, right? So this term goes to 0 if you have a saturated condition. And then you're going to have in here, and the port air pressure is going to be equal to your port water pressure. You know, if you have, it's the same pressure when you have saturated conditions, right? And therefore, the general case becomes the special case of saturated soil condition. And that's the important thing for this equation. So that's the shear strength. You're going to need, these are your soil properties, C prime, phi prime, and phi b. And basically, you can also do, which is, like everybody's doing, okay, what is cohesion? This one, that's what they call apparent cohesion, right? You're going to see your Holtz and Kovacs books, the very classic introduction to geotechnical, and they call it apparent cohesion, right? And now what he said, the true or total cohesion is going to be given by this value and this value together, right? So basically you can combine this value, and that's, again, I'm giving you the secret to do your slope stability analysis, all right? Using a program that doesn't include unsaturated soil mechanics, all right? You go ahead, find these parameters, add it to your cohesion, and that's the point that you put in there, all right? That's how it is. So basically, you can do a total cohesion, which is a function of the shear parameters C and phi B and the applied matrix suction in there, right? So you can combine those two. All right, so that's what I wanted to show you out of this. This is how you can represent that one, right? And now you have two stress state variables, right? The one which is the net normal stress, and if you just check, the same concept that we did with the Mohr Coulomb envelope, you can do a total stress envelope in here. But if you do have here a third, a three-dimensional, and he put it always on that direction. I like to put it in this direction. But anyway, when you have suction equals 0, you are on your saturated case right there, right? Saturated case, right? So these first in front, more circles below are for a saturated element. And that's your envelope for a saturated element. All right? Now, if you increase your suction, your more circles are going to be, this one at the same confining pressure, it's going to be bigger. You're going to get, because of the contribution of your suction, right? And what is the contribution of your suction? Then you're going to have in here, on this axis, the C value that you got, which remains constant during the whole C or 0, plus the contribution of your suction in here, right? Order minus forward pressure, tangent phi B, and then you're going to have higher. So as you increase your suction, the same more circles can be seen to be increasing, right, in size. And then if you just put everything on one plane, basically it's going to look like this, right? Right? It's going to be looking like that if you just put it in a two-dimensional plane. So but basically the suction will create that extra plane that you can just draw like that for simplicity, okay? Well, as the pore pressure becomes equal to the pore water pressure, yeah, that's for the first one in here, and the failure envelope has a slope angles of phi and phi B with respect to the net normal and the matrix suction respectively. Okay, many people measuring phi B. This is, like I said, it's important to understand now to know what it is, and most of them have found that, yeah, when you have the phi value for different soil types compacted at the same water content that for the phi B, and then looking at the phi B values, all of them, the phi B is less than the phi prime. Okay, so the contribution is slower going up. There are numbers in there for some clays, silts, tilts, and so forth. And it seems consistently working on that. So the shear strength, if you just check the shear strength versus suction plane in here, that you can see that the shear strength will increase with respect to suction, and it's going to be defined by the phi prime, phi B angle. Now, this is debatable. I'm going to show you some data that it just give you otherwise, and actually the same Escario data that you saw from the 1950s or 60s shows that there is some nonlinear variation of that, okay? And again, you can use it as a total cohesion in an unsaturated soil if you want to use the theories that do not include the phi B value right there, okay? That's what I will show you, like the increase in the shear strength as you increase your suction value. Now, how we measure either in the triaxial machine, like I showed you before on the history, or we measure it in the direct shear machine. Then the equipment needs to be modified. You need to change, for example, the area entry disc at the bottom, or put a colloidal membrane on that, or you have to encase your direct shear to sustain your ported pressure. For example, you need to do it in a chamber, right? So there are modifications that you can do for that. There are also triaxial apparatus that if you cannot modify them, you can do some stuff, right? Some stuff to figure out what is the suction. And you can test several samples of non-suction. So you just put your sample, for example, in a place when you can reach a suction value. And wherever the suction value is ready, you just translate it, right, to your triaxial machine and do the test, okay? That is good. I mean, the triaxial test, the samples are like this. So, to do that one is have you done that, Professor Barat? Have you equilibrated samples this big for suction before putting in a triaxial machine, or you have done them directly on the triaxial machine?
We didn't do suction control time.
No, you haven't done that. Yeah, that's not an easy thing to do. Totally not easy thing to do. But if you are using the small direct shear testing, that's what I'm doing right now. Basically, I can put it on the cell, the Friedland cell, right? You apply the suction. Wherever you know that the suction is ready, get this one, get to the direct shear machine and shear it, right? Now you know what the suction value is. Okay, so you can do tricks for that, to figure out what this one. Another one that we've done is like compact the soil at optimal moisture content, for example, okay? And you let it dry or let it wet, let it dry or let it wet. And you have separately find out your saltwater characteristic curve, right? So basically, if you know what is the moisture content of your sample, you can imply your suction out of it, right? And then being able to share your sample and imply the suction from the saltwater characteristic curve. So there are ways of doing this thing without modifying this one if your laboratory doesn't have the capacity for that yet, right? The tests are usually longer for saturated conditions. Why? Because now you're going to have to consolidate your sample. And remember, the consolidation is a function of your unsaturated hydraulic conductivity, which is much lower, orders of magnitude lower than your saturated guy. And therefore, you're going to have a longer test durations. Tests are more demanding, and we're going to go for that in a minute, because now you have two phases, the water phase and the air phase, right? The water phase and the air phase. And now the water phase can be drained or undrained. And now the air phase can also be drained or undrained. All right, so you do have those two phases to control the drainage condition. And the triaxial set must be modified in order to measure and control the air, which is expensive, and that's why predicting models are usually desirable, right? Desirable. These are the tests that I check with Bishop. He said, okay, we can do the same test as we did for saturated salt. We can do consolidated drain test in which both the water and end phases, you need to understand that when you do unsaturated, you need to think on both phases, right? Think about the two phases. Water and end phases can be drained during the direct shear on this one, and the volume change during the shear can be measured. When you have a constant water test, this is the one that I usually do, okay? Basically, the air phase is drained, okay? You can do this one, drain, or control it that way, while the water phase is undrained. So you then get the water out of it, but the pore water pressure can be measured, right? The pore water pressure, because you have an undrained condition. When you have an undrained condition, you can measure, right? When you have a drained condition, you are controlling, right? You are controlling. Or you can have a consolidated and drain test with pore water pressure measurements in which the air and water phases are sheared in an undrained mode, and you measure the pore and air pore water pressures. And they are consolidated and drain tests, UU tests, specimen is tested in similar way as the saturated specimens. They determine water content that you need to do. This is a total stress kind of analysis, right? And the unconfined compressive stress, that this has been used forever also. Total stress analysis when you're, confining pressure is zero and then you just shear it. Obviously, the only soil that you can test is the one that can withstand with no confining, right? So no sands are allowed for that. So the direct shear test seems to be superior for testing unsaturated soil due to the reduced length of the drainage path, right? It's a little bit easier for that. Faster equalization. But even though this something like that can take 3 days per test, okay, and actually I don't consider this to be a long time. I've been taking more than that for sure. But there are the same problems associated with direct shear, right? There is stress rotation, there is only strength parameters are failure can be obtained. You can't just do much about that, but you can imply some data out of the direct shear testing that are important for us. This is what we're doing right now in this one on a direct shear testing machine, and I just, my student Kalani, she's from Sri Lanka, and she's doing a tremendous amount of work on trying to figure out the direct shear testing for different matrix suction conditions and also for interface between geotextiles and the soil, so that I didn't bring the geotextile in here, but because of the topic, but basically she's using a couple of soils, get the grain size distribution, Atterberg limits, everything for that soil. And basically this is the kind of data she's obtaining right now. She said, please tell them do not publish this one because I haven't published, right? So this is unpublished data, but basically it's a different suction values. She put water content in here and she put the suction in here. This one, we're trying to go as dry as we can on those samples, right? As dry as we can. Because you can see on expansive soils, silty materials that we don't have data that goes more than 100 kilopascal, 120, 200 kilopascal. Well, clays have more suction than that, right? So that's what we're trying to do, is to figure out the whole range of suction values for that. So we're drying it very much. And this one is for the frost heave soil, which is a silty, is a CL value, I think. It's a CL's ML. The other one is a CH. And this is the data. You see, this is the saturated condition. This one is the optimum condition. And they're very close to each other, and they're parallel, like Fred Land and many have reported on that. But when you start getting into lower water contents, that deviates from a linear relationship, okay? So the phi value starts pretty much, the phi B value we can imply from here, but only to the optimal moisture content. Now she's making more samples in here because I'm interested on that. And then you start looking at that kind of variation when you get into the dry condition. So we jump to the expansive soil, and it's the same thing, saturated condition, up the way to the optimal moisture content, you can get very good linear relationships and more or less parallel to each other. So that's great. That's what is being reported. But again, when you start jumping into a much higher suction values, you're going to see a deviation from linearity on those things. So this we found this to be important because there are a couple of researchers that have found that, right? And to see we can just tune up that equation that I just showed you before, right? The phi B equation. This is the shear strength variation in terms of suction. If you put it in a arithmetic scale, you're going to see how it just, is a value here that is kind of jump up, and then it just slow down as you increase your suction value. Same thing here. So there is a point when there is no more contribution of soil suction appears to the shear strength of the soil, at least for this one. And again, there are some, if we go for a sand material, right, the third soil, I'm very sure that, very soon in here we start just looking at the going down strength right there. But this is also important. It's not the optimal moisture content. It seems to be a little bit less than that, right? So we need to figure out what is the relationship in there until what contribution and why we got this leveled out. This is the phi B value that she's finding. Okay, that's the variation of the phi B angle with salt suction. As you can see, it's a constant value, at the beginning, equal to the phi sat, the phi prime. But then as you start increasing your suction and you're passing the air entry value, seems to be like, you just go down with the contribution of time. So this is what we're looking at. That I think is interesting data to show, and it's a very good set. It takes a long time to get a good test well done. Okay, so based on that, she's proposing some model equation, like the Friedland model that I just showed you. With the data we got an R square of about 73, and if she just put a power model for the suction value, right, instead of a phi B value here only, she put up a power model in here. She starts finding that the R square increases. Okay, and she's looking at exponential functions in here, and that's what you do. You're modeling different scenarios to figure out. But definitely, we're trying to figure out if that model can be improved with a simple model as as something like this. And it seems like we can improve some of the model. Obviously, this one is for a particular set of data points and soil types, right? We're going to need a bigger range. So hopefully if you guys have any data on sandy materials or something, we can all contribute it to, some data for the literature. All right. So this is how we measure, right? That's how we measure. This is how we work on these equations to figure out what there is the shear strength. And basically, if you don't have that, how are you going to estimate it, right? How are you going to estimate that? Well, there are some estimated values, and again, the first one that was shown and has been, very famous, and again, I gotta bring it in here because it's part of the history of unsaturated salt, is the Bishop equation. This is a predicted value. Why? Because he gave us values of chi for different salt types and different degrees of saturation, right? So that's our predicted values. So you got your chi value here, but again, this is that means that the contribution of suction and the contribution of normal stress are the same, right? For tangent phi prime. Anyway, but this one is one of that. There is another one. There are several equations that are empirical or based on the saltwater characteristic curve and the saturated shear strength parameters, right? In all of them, phi prime is equal to phi B for matrix suction less than the air entry value. That's what we found also in the laboratory now. There is a point, this is the air entry value. There is a point that, starts changing in here. Plastic clay seems to be going in this direction, like power. When you get silties, I found also a little bit bumping down, but, sandy salt definitely goes down after you just get the salt drier and drier. There are several equations that can be predicted, not only the Friedland. Vanapali did a great job, and I think, Professor Vanapali has been here also. He's an amazing researcher and has done a lot of work for unsaturated salts. Villar, okay, Khalili, okay. There are many, many researchers, and I gave you those equations. If you want to try different models for your data, it's an important that. These are, of interest to me are the Vanapali, because there are predicting using the saltwater characteristic curve. Those are the parameters for the saltwater characteristic curve. This is another kappa parameter in here, which he and Professor Friedland gave values. Where is? Didn't bring them. Okay, here we go. Gave values based on plasticity index, right? Which I think I found them interesting, right? Because it's, those are estimated values. You can find, this is Marinho, this is the group from Brazil, which is actually great too. So they do have a lot of gray material in there, where if you have the plasticity index of your soil, you got your kappa value here, and then you apply this one to a volumetric water content in here, and then actually you have the rest of the parameters ready. So it's very interesting equation that you can use. Okay. This is Houston, 2017, she uses the equation by Fred-Land, and basically what she did is she found a ratio for phi b. Okay, so we're gonna jump into here, and basically she found kind of to the air entry value, definitely this thing is a constant, and then she found a hyperbola going down in which the phi value is a function of two parameters, A and B. This is your suction value. And she found the A and B based on, I didn't bring the B, should be here. Yeah, B is a function of phi prime, found it in here, and A is a function of grain size distribution. So this one is, I'll give you a summary of the methods, the method that Professor Houston also put together for that. But basically you go to the laboratory, you determine your C prime and phi prime, right? Your saturated parameters. Then you estimate the hyperbola fitting values, A and B, from gradation data or whatever you need for that. And basically found the phi B for that and just apply the equation. And then you got it, right? At least you have an equation that is much better than using a saturated soil equation in a problem that you needs to improve. Okay. Applications, there are many. Again, I just brought you some soil stability analysis in here. But basically, this one is what we do on this, all right? There are some methods that have been starting including those into the program, but I haven't seen like CPH analysis. You can do an unsaturated CPH analysis these days with Plaxis, CIPW, all other programs that everybody are putting together. For this, I haven't seen many of variations that include phi B. There are some stuff in there, but basically, the method include, for example, to solve the entire wedges, the free body diagram, or method that divide into the method of the slices, or optimization techniques that you got in here. So for example, I just want to show you how you can modify a normal slope stability analysis, right? In which you do have a wedge and a full free body diagram in which you have here, for example, the slide, right? You have your external forces, lateral and normal forces. You got your W here, and you got your shear force and your normal force, right? This is how we do that one. And then you're gonna, and this is beta is just the size of that slice. Alpha is the slope at the middle of every one of those slices, right? So this one is a normal configuration for you to do a slope stability analysis, right? So once you have this one, and basically what you need to find out is your shear force in here, right? That's your shear force. Okay, so what we do with the shear force is, as you solve your free body diagram, you're going to find that the shear force is the length of the slide, and you divide it for the factor of safety. That's the one that you use for putting in here, and then you put, the stress, right? The stress multiplied by the area will give you the force, right? And here is your stress, and you can just put the Fred-Land and Sin equation right there, or any equation that you want or need, right? So the mobilized at the base are going to be just a function now of the normal stress, the port wire pressure, the net normal stress, the cohesion, anything you have, and the port wire pressure right there, right? All of these act to this point. And then this is the equation that you can use. Now, consider that the matrix suction as part of the cohesion. And I think this is the best way that you can go, right? You go ahead and say, okay, this equation, the whole equation that you have in here, I can combine C prime plus the contribution of the suction into a total suction value, total cohesion value, and then in here you do have the shear force. So you can use the C value, that force in here, and the shear forces, the two forces that any computer program will allow you to enter, all right? So that, you can contribute it for some of the areas, the different unsaturated soil conditions that you're gonna have. So this is what I believe is that's what I've been doing, and the results are okay until we found programs that include tangent phi B or other models available in here. All right? So do you guys have any question for that? Yes.
Yes, ma'am. I have a few questions. The first one is about that Phoebe value that you have presented. You have shown some results from your PhD student. Can you please go to that slide? Phoebe variation with suction. Yes. So it seems Phoebe decreases with suction, increasing the suction. So yeah.
Correct.
Does it mean to say that the contribution of matrix section will be maximum at fully saturated state or
Correct.
before the area?
Not the fully saturated state, but there is contribution, is increasing. The contribution will increase linearly, right? Linearly, the Phoebe will be the same, right? The Phoebe will be the same. So if you plot shear strength versus normal stress, versus suction, we don't have that one? Shear strength versus suction, right? Okay.
I think if the Phoebe is, or the initial shear strength is increasing with matrix suction, Phoebe is constant, which is equal to phi dash.
Yeah.
Mm-hmm.
Later on, Phoebe is decreasing, it will go to negative also. So that's the actual exactly problem. Initially, Bishop's equation was criticized, saying that the chi value is not constant. Chi is also dependent on suction or water content. Initially, Fredland thought it's a phi is constant. With 3 data points, he thought it's going linearly, and he proposed that expression.
Mm-hmm.
Later, it is realized that phi is also dependent on either water content or suction. Mm-hmm. That's why it boils down to the Bishops.
Mm-hmm.
So reason is, if you go back, this results if you see, the nonlinear effect that is coming towards the higher suction is because.
No. Okay.
I'll just finish my this sentence.
Yeah.
Initially, when the higher moisture content if you have in the soil samples, you are trying to fit using effective stress principle or whatever C dash, phi dash, all those things. At very low moisture content, do you think you can use C dash and phi dash to fit that? When soil is nearly dry conditions, it behaves like undrained. Water doesn't come out. Same soil, when the suction is changing or when the water content is changing from saturated to dry state, the behavior changes. If you try to shear the sample when the soil is nearly saturated conditions, drainage takes place. Water can come out. But nearly dry state, water cannot come out. It behaves like undrained manner. Right? There is a phase transformation that takes place from air to water or water to air. Either vapors are formed or air is actually getting into water as solute. That is what is happening at higher suctions. So therefore, fitting everything with one single equation, which is based on C dash and phi dash, is the problem.
That's correct.
Yeah.
Now, what happens when you test a saturated sample in an undrained condition?
Yeah.
So you are not moving water in and out.
If you have a saturated sample, if you are doing an undrained test, we never use C dash and phi dash. We only measure undrained shear strengths. We measure if your pore valve pressure is estimated, then we have effective stress we have to bring. But Fredland one, you cannot segregate effective stress concept. You can only use sigma dash there instead of sigma, and then you have to bring there.
You can, well, yes, I think this is a great point, but I think for any suction value, you can always measure what the forward pressure or the suction contribution is given, right? And that's why we don't put them all together, right? We put them in 3 dimensions, right? So you're right, when you have a saturated condition, then you have your total stress analysis in here, or the total stress analysis in here, and then you got a pore water pressure in here, and this is your effective circle, and this is your total circle, right? This is your pore water pressure. Okay, basically, if you do that, if you measure the pore water pressure, you can get CMV. You can measure fear. And I know that you said on the one of your first lectures that you know, that it's either UU or CD, right? So you can.
CU or CD, not, I don't choose UU, by the way.
Oh, you know.
I don't use UU.
So yeah, it's CU. So you can get the contribution of your suction or your pore water pressure when you have saturated soils easily, right? When you start getting into the dried samples, you're right. You know, this more circle is going to be increasing in here, and whatever contribution is in here was because of the suction, right? Because of the suction value.
See, measuring suction at shear plane during failure is like kind of impossible.
Yeah.
The reason is you are trying to measure. Most of the tensiometers don't work beyond 100 kilopascal because of vaporization. Because the vapor pressures are the total pressure reaches to vapor pressure, so cavitation takes place. Same thing happens. The air is not full air. You just to say that UM and SUW I'm trying to measure. Now some other things are available in the vapor, water phase, and air is available in solute. So measurement is a big problem. Although we are saying that I'm controlling suction, you are controlling suction at just two ends.
Well, it's the
Right,
same.
so-
It's the same thing that we had for any soil, in which we figured out that the volume change is occurring or not occurring. When you do have undrained conditions, it doesn't mean that the moisture is not moving from this point to this point, or from this point in the shearing failure to another point. What you do is to do an overall estimation of that the sample, you're not going to get it out, right? But it doesn't mean that the water will be moving, unless you're going to tell me that the student did a wrong
I'm not judging.
equation,
No, no.
a wrong test.
I'm not judging your students' capabilities or anything.
No, no,
I'm
no.
just trying to tell that, in saturated state, when you're doing undrained test, I'm sure the water is moving. Imagine water is available as a lens around the particles at a very high suction value or very low degree of saturation. Do you think water moves that freely? Where if you estimate the hydraulic conductivity is nearly compare -14, -15.
It doesn't move.
So that's the condition, right?
That doesn't move.
Yeah, yeah.
But what I'm saying is for the saturated condition, if you have a saturated condition, if we consider that sample to be undrained, on the shearing zone, it's not undrained.
That's what I'm saying. Near to saturation, even Bishop's equation works very well. Correct? Yeah. So all of them work because.
Oh, but just for saturated conditions.
Yeah.
85 or plus is
Yeah.
what we said. Those are all great points. But it's absolutely right. So that phi varies. There are many reasons why phi varies or not. But, Professor, but it's true that, probably there is not only those two, that we have to measure that, right? There's going to be more stuff that we need to add in there as we get the soil, the menisci much smaller and smaller. Other forces are acting in there that are just different, okay? That are contributing to your shear strength, right? But this is if we are trying to beat the most famous equation that is in there, we're going to need to start by trying to figure out what they're doing. All right. So anyway, great conversation there. Any other questions?
Danish question. I don't know
Yeah.
what he wanted to ask.
Well, Danish question was, but still a contribution. There is a contribution up to that certain point.
Right.
And then we're just flattening out, there is no contribution, right? There is no contribution of the shear strength there is no contribution of the matrix option to shear strength pretty much.
Okay.
Okay.
And if you could go back to that earlier slide,
To the
previous one.
previous slide. Previous slide.
Before this one.
Oh, right here.
Yeah. Here, the normal stress that is shown here up to 80 kPa. I was wondering what can we expect if we go beyond 80 kPa? Higher normal stress.
Higher normal stresses. Material crushing, probably. Okay, so you're going to have
Okay.
much more, Well, if you are just figure out what the shear stress, the normal stress contributes to the shear stress is, right? You know how much load are you going to be putting there, and you're going to start increasing there. I guess what people that have done that have find out that you start, not for those oil, but for more granular material, you start getting into the crushing, right? Into the crush, and the more envelope start going kind of down.
Okay.
Kind of down, right? It's not a linear anymore, or flattens down.
Okay. And
Do you have any? What again?
Our ductile material behaves like a brittle medium at higher normal stress.
Yeah. Okay. So exactly, you can get some straightening in there too.
okay. And you mentioned that the right-hand side figure is for expansive soil. That one.
This one is for expansive soil.
Okay. What was the PI value or plasticity index in that one?
It was rather kind of middle. PI is 32.
32. Okay. But these are all direct shear tests, right?
Direct shear test.
Okay.
But they're being consolidated. Consolidated separately to the normal stress that you put in there. Okay. That's why those things shows they should be kind of flattened down, right?
Right.
Right. But they were consolidated first, and then you just move to the direct shear machine.
Okay. Yeah.
All righty.
Adding to that question, the next slide, can you please go?
Here we go.
The next one. So, how did you measure the suction, the measurement device, like for lower suction values?
Low suction values, these ones? Okay,
Yeah.
how we measure low suction values? Okay, so what we do is we just get the sample, we put it on the pressure cell, and we just equilibrate it to the suction that we want, or to the pretty much the water content that we want. So we know how we estimate, we compacted the sample always at the optimum moisture content, okay? And then after that, basically, we just put it on that and we start, letting it dry by applying a particular suction, right? When we know how much water is going out and we know that the water content is what we want, we know the suction value, because you got the saltwater characteristic curve, right? So pretty much what you do have is the saltwater characteristic curve data. Water content. Did I do? It's this one, right? Water content versus suction, right? So what we got in here is I want this to be at this particular water content, say gravimetric, okay? So that's the guy. So this is your suction for that point. And you get that suction value, and then we just put it for the Phoebe value. So we didn't we haven't we did not modify the shear strength cell. We did not. Okay, we just shear the sample at a particular suction value and a rather high shear rate. That's another thing. It's a high shear rate, so we avoid any drainage condition that we have, right? Any drain, and that's all that it doesn't drain in 20 minutes. That this lasts at all. So that's how you do it. So we put it on the saltwater characteristic curve. We figured out the suction of the water content that you want to test. Once the sample is at that condition at that point, you put it on the shear strength device and you shear it. So you shear it like that. Okay. All right. Any other questions? We got a break going on? Ooh. 10:30? No, what time we start? 10 to 11?
Break is at 12:30. 12:30, right? 11:30. Oh, 11:30. Huh.
So we are on a break, right? Right now. I'm sorry, guys, but it was his fault, not mine. Yeah. All righty. So I'll see you in a bit to continue that, with the